Okay, so in this video we're going to introduce the concept of a vector equation of a line, the parametrized vector equation of a line. And we're going to do this in R2 in two-dimensional space, just to sort of introduce the concept in a setting that's more familiar and sort of see the correspondence between that and the way that we've been representing lines up until now. But what this is really useful for, because you may be thinking, why are we doing it this way? We have this perfectly good way, which you can see here, this y is equal to mx plus b form of a line. What's wrong with that? Well, in 2 dimensions, there's actually nothing wrong with that. But when you go to 3 dimensions, and then even higher dimensions, if you're going to do that, we can't do this anymore. So we need different ways to represent lines, and then later planes. And this is a really big thing in vectors. This is sort of where a vectors course begins to pick up. And so it's really important to have a solid understanding of this. So as we can see here, we have the y is equal to mx plus b, or the slope y-intercept form of a line, which hopefully we recognize as having a slope of m and a y-intercept of b. And this is all that we need to determine a line uniquely. In 2 dimensions, a line is determined by either 2 points or a point and a slope. Of course, the 2 points give you the slope. In this case, we've represented the line as the y-intercept, so it goes through the point 0b, when x is equal to 0, y is equal to b, that's where it crosses the y-axis, and m, the slope, this indicates that if we go over by 1, we're going to go up by m. When x goes over 1, we go up or down by m, depending on whether m is positive or negative. In this case, it's positive. And so this is great. We can represent this line this way. That's terrific. But there's another way that we could represent this line. We could also, let me sort of unwind this. We could also say, all right, what if instead of this, I wanted to say, take a point vector on the line. So this is a vector, we'll call this P0, which is a position vector on the line. And then I'm going to take also what we call a direction vector, which is a vector, we'll call this D, in the same direction as the line, and I'll start out at P, or P0 here, and then I'm going to add multiples of this direction vector. So I'll go from P in, well, I don't want this to be green, not orange. D is green, we've established that. I'm going to go in multiples of D from P. So this is for some value, say T of some t in the real numbers. We use usually t and s for our parameter values. T is called a parameter here. If I add t times d to p0, I get to this point. If I get another value of t, say like a negative value of t, I come back, well, let's make this highlighter instead. There we go. I come back in this direction. This point, and I want this to be a lot smaller, this point is going to be P0 plus, say, we'll call this one T1, and this is, say, T2 times D. Or better yet, let's call this negative T times D. So this will be minus T times D, to show that this is a negative direction. And hopefully, if this looks sort of weird, go and check out the videos on vector addition. That's one of the reasons it's so important to have a solid understanding of vector addition, is because it leads into stuff like this. But the idea is that what does adding these vectors together do? Well, it determines a point. Each one of these, adding this multiple of this direction vector to the position vector, determines a point on the line wherever we end up. And we can think about this as t varies over all of the real numbers. T is in the real numbers. We can think of this as tracing out this line. We call this, now we're going to say this line is L, and L, we use this colon and then an equal sign to say that L is defined to be equal to P0 plus T times D, and T is in the real numbers. And this is the parametric equation. The parametric equation, or sometimes, I think most of the times called the vector equation, because P and D are vectors. we also, and we'll see this when we do it in 3 dimensions, we can write this in what we call the parametric equations, plural, of the line, which is where we actually look at it on a component by component basis rather than just P0 and D, the vectors. So this is the vector equation, but both of these use a parameter, which is the important thing here, is that we're not specifying a point and a slope. We're using a parameter to trace out this line. But now we see that the same way that the line in slope y-intercept form down here, and I shouldn't use pink to highlight pink. I should use maybe green to highlight the pink. The same way that this line was determined uniquely and completely by the slope m and the y-intercept b, well, in parametric form or in vector form, it is now determined by entirely and uniquely by the point P0 and also the direction vector D. And I should probably, I'm going to change the colors so that we can get a kind of a correspondence here, because I want to stress sort of the kind of analogousness of the position vector P0 to the y-intercept B. This tells us that there's a point on the line. This tells us a particular point on the line. I know that the point P0, when t is equal to 0, is on the line. Same thing here, when x is equal to 0, the point 0b is going to be on the line. So in vector equation world, the position vector is kind of like the y-intercept, sort of playing the same role. Similarly, the m, the slope of the line, plays a sort of analogous role to now the kind of the corollary to that, or the counterpart to that, in vector equation world is the d, the direction vector. This tells you the direction in which the line is going. If I increase t, what direction do I go on the line? Where is the next point on the line going to be? If I go over a bit, t isn't really going over the same way that x is going over, but it's kind of similar. It tells you how the line goes, at what angle it's going up from that point. How is it moving away from the point? In what direction? M does the same thing. So and this turns out to be a very useful way to think about lines, because, like I said, when we get into 3 dimensions, we can't just say, well, I have a slope and a point anymore. That doesn't work. In 3 dimensions, we need actually more than one number to determine a direction. So saying what is the slope of the line doesn't really have the same kind of meaning that it does in 2 dimensions, right? In 2 dimensions, if you go over by some amount, you go up or down by some amount, and that's it. In 3 dimensions, now all of a sudden you can go in all sorts of different directions. So we need an entire vector to determine the direction. So I want to just hopefully this is clear. I want to just wrap this up, and I'll get rid of this random little thing up there, and in the next video, because this is getting a little bit long, we'll go into 3 dimensions and see what the vector equation of a line in 3 dimensions looks like. I want to see how we can go back and forth, because this is a thing that they can test you on in high school in a vectors course. How do we go back and forth between the vector equation of a line and, say, the slope y-intercept form of the line? We'll start out with one and get to the other, and that will let us look at the actual components of the vector, as well as what so the parametric equations, where we get a little bit more granularity there. I got rid of that. Okay, so suppose I have the line y is equal to, well, that's a terrible m. Y is equal to mx plus b, and I want to write this in vector form. Well, what do I need? I need a position vector, P0. This is going to be equal to P0. And then I need a direction vector, D, which is going to determine the direction of the line. So the position vector, by the way, is not unique. The direction vector is not unique. It's a little bit more unique than the position vector, because the line is only going to go in one direction, but it can go in forward in that direction or backward in that direction. So for any direction vector, it doesn't matter how long it is, and you can multiply it by a negative and it can go. So this one would be, if this is like D, well, if this is D, then you can multiply d by 2 or something and get 2d. That's another direction vector. Or you can go in the negative direction. You can go to negative d. And these are all perfectly good direction vectors for the line. But so the d is not unique, but they all go in the same direction or the opposite direction. The position vector is, you have a lot more freedom. Position vectors is just any vector starting at the origin that stops at a point on the line. That's a position vector. And that's a position vector. And that's a position vector. And that's a position vector. There's a lot more position vectors, and they don't have the same direction. They're not multiples of one another the way that the direction vectors are multiples of one another. They all start at the origin and terminate on the line. So how are we going to find a position vector for this line? I mean, we could just plug in a value of x and get out a value of y and say it's that corresponding point. Easiest way, because we have this thing in slope y-intercept form, is just to use 0b. We can just literally take as our position vector. This will be, let me make this a little bit smaller so we can have a nicer arrow. There we go. This is 0b, or if we want to write it as an upward standing vector, which is more sort of common at the university level. And so it's a good idea to sort of get used to this now. When you start doing linear algebra, they're all like that, and you'll see why when we get there. But this is a perfectly good position vector. That's a pretty obvious one. What about a direction vector? Well, once again, we have it right here. The slope tells us the direction of the line. The slope m tells us that if we go over 1, we go up by m. So what is this vector here? If we were to put this at the origin, like that, this is the vector 1m, or 1m. This is a direction vector for the line. And again, any non-zero multiple of this will work just fine, but for simplicity, we can say L is defined to be equal to 0b plus t times 1m. Or if you're really committed to these, really attached to these horizontal vectors, which I do in high school, I can write this as it's defined to be 0b plus t times 1m. So that is the equation of the line. That is the vector equation of the line. Suppose I wanted to go in the opposite direction, so to speak. Suppose, and by that, I don't mean direction in two-dimensional space. I mean, suppose that somebody gave me a line in vector form. So let's say I have, well, that's much bigger than I intended. Suppose I have a position vector, p0, which is x1, or let's keep the subscript the same, x0, y0, or we can write it as x0, y0, and then suppose it's traced out by, they give me this direction vector, we'll say this is d. So, and let's just actually do that. Let's go in both directions from here. There we go. So this is the line. This is the line in vector form. This is d, and let's say d is equal to d1, d2, or again, I want to put in both d1, d2. So this just really emphasizing that the x is in the top, and then the y is in the bottom here when you stand these vectors upright. So L is x0, y0 plus t times d1, d2. How could I get the y is equal to mx plus b version of this line? How could I put it into that form if they wanted me to convert the other way? Well, the first thing I think I want to do is get the slope. I want to say if I go over by 1, how much am I going to go up? What is the m there? What is that m going to be? And this is information that I can get directly from the direction vector. This is my direction vector d. if I look at D at the origin here, D is D1, D2, or D1, D2. What does this mean? It means that if I go over, well, I wanted that to be a highlighter. I'm bad at this. If I go over by D1, and let's make that a little bit darker. There we go. If I go over by D1, now I go up by D2. D2 is the y-coordinate. D2 is how much I go up or down, depending on whether it's positive or negative, after I go over by D1. So D2 is the rise, and D1 is the run here. My m is going to be D2 divided by D1. That's how I get the slope of this line. How do I find the y-intercept though? However, this is a little bit trickier. I have this point on the line which is 0 and b. So the x-coordinate is equal to 0 and the y-coordinate is equal to b. How could I figure out what that b value is? Well, I think, all right, I have this point P, which is x0, y0 here. This is where I start. And in order to get to this point, I'm going to need to go by some multiple of d. I'm going to need to add, and this is the d here, I'm going to add t times d to p or p0 here, and that gets me to this point, 0b. And so the idea is I need to figure out what that t is that is going to get me there. How far in the d direction do I need to go, positive or negative multiple, in order to get to this y-intercept? And I probably should have, just to be circumspect, labeled this is the y-axis and that's the x-axis. So how do I do this? How do I figure this out? Well, I look at the x-coordinate, whoa, and I highlight it in a nicer color, and I say, all right, I need the x-coordinate, which is here. It's x0 plus t times d1. I need that to be equal to 0 if I'm going to be at this point, at the y-intercept. So I need x0 plus t times d1 to be equal to 0. This happens if and only if t times d1 is negative x0, if and only if t is equal to negative x0 divided by d1. That is the t that makes, when I add that multiple of t, or that t multiple of d, the direction vector, to the position vector, that gets my x-coordinate to be equal to 0. So all I have to do to find the y-coordinate of that point, which is the y-intercept, is plug this in to the vector equation, multiply the d2, the y-coordinate of the direction vector, by that t, and then add it to the y0. So I get my b is going to be y0 plus negative x0 over d1 times d2. That is going to be the y-coordinate, or the y-coordinate of the y-intercept, or just the y-intercept. That is the number, the y-intercept, which is the y-coordinate of the point where the line intersects the y-axis. And as I'm doing this, I'm realizing this is very abstract and probably a little bit confusing. So let's do an actual example to sort of illustrate this point. Even though we're going kind of long on time, I think it's better than leaving it here. This is y, this is x. So suppose I have the line y is equal to 2x plus 3. Let's keep it nice and simple. So it's going through 0 and 3, and it has a slope of 2. So that means that if I go over 1, I go up by 2. So let's connect that. And again, this is my point and slope determining the line uniquely and completely. It goes like that, and then it goes like there, if this will complete for me. All right, so I want to put this into vector form. Well, I already saw I can pick my position vector And it's a good idea if you're wondering, by the way, do I have to pick the position vector to be the one that connects the origin to the y-intercept? No, absolutely you don't. Great exercise to go and come up with a different representation of it. Try to find a representation of this that uses a different position vector and a different direction vector. But we're just going to go with the easy, obvious one here. So P0 is going to be equal to 0, 3, or 0, 3. And then what did we say about D, the direction vector? Well, it's going to be 1 and then m, the slope. So 1, 2, or 1, 2. So the line in, I can probably do a little bit better out than that. The line in vector form, or the vector equation of the line, is going to be 0, 3, the position vector, plus t times 1, 2, the direction vector, that's P0, that's D. Or again, if we really are attached to that horizontal orientation, although again, I think it's the sooner you get away from that, the better, because they stop using that in university. It is going to be 0, 3 plus t times 1, 2. Now, what if we want to go? I just really stop for half a second there to let people take that in. What if we want to, now let's immediately go the other way. What if we're given, say, a vector equation. Let me just make something up. L is defined to be equal to, say, 1, negative 2 plus t times, 3, 1, something like this. Let's plot this. Let's start out at, well, this point here. This is again in the horizontal. This is the x is 1 and the y is negative 2. So I'm going to go 1 and then down to negative 2, and I end up here. This is P0 is my position vector, and then this t times the direction vector is telling me that this is going in the direction of, I should do this in a different, I almost started to talk about the slope, but this is going in the direction of the vector 3, 1, or 3, 1, vector that goes over 3 and then up 1. And so again, and now it's a little bit easier to see how I got the slope. Before it was sort of abstract, talking about x zeros and y zeros and everything. Well, this thing, it goes over by 3, and it goes up by 1, so the slope is equal to 1 over 3. This is the rise over the run. And the y-intercept, well, how do I figure out the y-intercept? Again, this is the slightly trickier part. Well, I want in the, let me do it, let's sort of merge it. I want the x-coordinate, which is 1 plus 3t. I want that to be equal to 0, and then I'm going to figure out what the y-coordinate is once I solve for that t. So I want 1 plus 3t, the x-coordinate of the y-intercept, to be equal to 0. Well, this happens exactly when 3t is equal to negative 1, or when t is equal to negative 1 over 3. That will make my x-coordinate equal to 0. What will the y-coordinate be when t is equal to negative 1 over 3? Well, it's going to be negative 2, the y-coordinate of the position vector. So it's going to be negative 2, I'll do it up here, negative 2 plus this t value, which is negative 1 over 3, times the y-coordinate of the direction vector, which is 1. Or it's going to be negative 2 minus 1 over 3, or negative, let's do this step by step. This is negative 6 over 3 minus 1 over 3. So this will be negative 7 over 3. So this is telling me that the y-intercept of this thing is going to be negative 7 over 3. So I'm going to try to sort of plot this fairly roughly. Negative 7 over 3 is negative 6 over 3, which is negative 2, and then I'm going to go down by another third of the way. So this is roughly negative 7 over 3. This is my y-intercept. And then the slope is 1 over 3. So let me actually just copy this vector, which has the slope that I want, and bring it down here. And then I'm going to get roughly, if I can try to position it, there we go, like that. This thing is now going to trace out for me. This is the D. This is going to trace out for me this line, the vector equation of this line in both directions, like that. And there is my line. What is the equation of this line? This is y is equal to 1 over 3x minus 7 over 3. That is the y is equal to mx plus b form of this line. So that's how we go back and forth. That's how we convert. Great idea to practice this a little bit, because like with all things, it's in math, it's really easy to sort of look at it and say, oh yeah, that makes sense. And then when we go to do it, it can be a different matter. So it's great to do some practice, just make up some lines in both forms and convert them back and forth. And so hopefully that familiarizes us with the concept. And then in the next video, we're going to look at going into 3 dimensions and doing vector equations in 3 dimensions. And that's when it starts to become really useful.